The vector equation of a line. So you started learning equations of lines back in grade 10, but we did it into 2 dimensions, and this was probably the most common formula that you were used to, y equals mx plus b. So in the y equals mx plus b formula, it made a line because it had a slope and it had a y-intercept. The vector of the equation line is going to be somewhat similar. So I want to describe a line that goes through the points A, R, and C. And once I create a vector equation of a line, the nice thing about this is it's not only restricted to 2 dimensions, which y equals mx plus b is, but you can use it in 3 dimensions as well. So we'll be able to use this equation of a line to make lines in 3 dimensions. So a couple of things. We've got the points A, R, and C, and we've got our origin here. So the vector A is a position vector from O to A. R is the position vector from O to R, and C is the position vector from O to C. And if you wanted to go from O to R, you could go from O to A and then go from A to R. Does that make sense? And what a vector equation of a line does is it's just really a list of position vectors that end on that line. So if I wanted to pick a random point on that line, which in this case is represented by R. R could be anywhere on that line. What would I have to do? Well, I would need to know the direction of my line. So I'm going to call, in this picture, A to C the direction of the line. So if you know 2 points on your line, you can find the direction vector from in between those 2 points, and every point on the line will be in that direction. Okay? Secondly, if I want to find some random point on the line, oh, and by the way, the direction vector, I'll highlight it here as far as making connections to things that we've done in the past. That's kind of like your slope. The direction you need to go once you're on the line is kind of like the slope, because once you're on the line, your slope tells you how to find another point on the line. With an equation of a line, you also need some point to start off with. So the position vector OA is any point on the line, which is different than y equals mx plus b, but related. In y equals mx plus b, you had your y-intercept as a starting point. And then you could use your slope to find another point. You could use your slope, and that's how you might have graphed it in the past. If you were graphing y equals 3x plus 2, you would start with 0, 2, and then you'd use your slope 3 over 1 to go up 3 over 1, up 3 over 1. And you could find a whole bunch of points. Or you could go down 3, back 1. That's what the vector equation of line does, but instead of having a specific point like the y-intercept, you can have any point. So if I want to find a point on my line R, I could do it by first going to A, there's OA, and then heading in the direction of A to C by some multiple t. Right? Right now it looks like maybe about 2/5 of the way from A to C would stop at R. And if I went 4/5, I'd get to D. And if I would go -1, I'd get to maybe some point over here on E. And as I change the parameter t to any value, I would slowly get all of these position vectors along that line. And putting all of those position vectors together would create that line. Just like in y equals mx plus b, you could plot a number of points, and if you plotted every single point possible, altogether that would make the line. So to recap, the vector equation of a line any point on the line, maybe I'll write this as you choose any starting point whatsoever. You need to find the direction of your line. And once you have the direction of your line and any starting point, then any multiple of that direction will get you to any other point on that line. Okay? So for example, if you look at the floor, there's a bunch of lines. If I wanted to be on this line, if I start on this line and I know the direction is this way, if I go +2, that's like going 2 tiles up. -3 would be like going back 3 from my original point. +10 would get me 10 forward. But no matter what parameter of t that I use, I will stay on that line because I'm still going in the same direction over and over again. So in 3 dimensions, I have a point. I have a direction going this way. And as long as I go in that direction, any multiple of that direction, I will get all the points that make up that line. And each of those points will be represented by a position vector. So here's our vector equation of a line, and we change the c minus a just to a vector b, and we call it a direction vector. Now we can write it in that regular form, but we can also rewrite it with its components, and sometimes you'll see the components written separately. So in 2 dimensions, you would have a point x, y. You would have your direction vector b1, b2, and a point on the line a1, a2. Then any point on the line can be represented by a1 plus t times b1 and a2 plus t times b2. Yes. Then you would have a third equation. You would have an a3 plus t b3. Okay, so if I added this in, I would have a third component of that vector, a third component of my direction vector, and I would have a third parametric equation. So what the parametric equations are doing are just looking at a specific component, just your x component, just your y component. Now, if you took those parametric equations, if we take the 2 parametric equations that we have here, I'll erase the extra values. Can you see that you could solve for t by subtracting a1 and dividing by b1, subtracting a2 and dividing by b2? And by solving for t in both of them, since the t's are equivalent, you could equate them. And this is called the Cartesian form of the line. And there would be a third one if it was three dimensions. So we're going to see some interesting things that result from these 3 different forms. They'd all be equal. So here we've got 2 dimensions So we could think of this back in our old mathematics of y equals mx plus b. We know that it goes through the point 2, 5, and it's parallel to the vector 3, -4. So 3, -4 is our direction vector. So our vector equation of a line says take any point on our line. We have 2, 5 plus a scalar times the direction vector 3, -4. What makes a vector equation really nice is you're not concerned about finding a specific point like a y-intercept. You can just start anywhere. The parametric equations, that's when you look at specific components. Your component for x will be 2 plus 3t. Your component for y would be 5 minus 4t. My Cartesian equation would be solving for t. So you see in the first equation you could solve for t by moving the 2 over and dividing by 3. In the second equation I could solve for t by moving the 5 over and dividing by -4. So we've got our vector equation of our line, our parametric equations of our line, and our Cartesian equation of our line. Okay? And now, right beside all of this, we're going to do some grade 10 math. So if you have the point can't even write points in grade 10 anymore. Here we go. There we go. 2, 5. We have the point 2, 5, and it's parallel to going 3, -4. That would tell me that the slope of my line is rise over run, -4 over 3. It tells us that the line is going through the point 2, 5. So in grade 10 math, you learned 2 different techniques to find the equation. Technique number 1, which I find you remember more, because most people remember y equals mx plus b. If you know what your slope is, and you know a single point saying that when x is 2, y is 5, we could solve for b, and you get -8 over 3 plus b, add 8 over 3 to both sides, and this would be 15 over 3 plus 8 over 3. Your b value would be 23 over 3. So your equation of a line in y equals mx plus b form is -4/3 x plus 23 over 3. If you remember the point slope formula of the line better than y equals mx plus b, a reminder of the point slope formula is y minus y1 equals mx minus x1. See, you don't remember that one, right? It's just the slope formula rearranged. Okay? And so in this form, the x1, y1 is your point. Your slope is still -4 over 3. And you would have x minus 2, y minus 5, because your point is 2, 5. Okay? Multiplying this out, Add 5 to both sides. It's the same equation. Yes. I can scroll up. So, how far do you need to go? What's that? It isn't on that line, but it tells us that it's parallel to that vector. So we go to 2, 5. What we're looking for is how does 2, 5 with that same parallel slope, what's the equation of that line? 2, 5 is on the line. Okay. So, some things to compare. Looking at the y equals mx plus b formula, any kind of mathematics that you would do with the y equals mx plus b formula would involve some fractions, which by now isn't probably too bad. It's just more annoying than well, it's just tedious and annoying as opposed to incomprehensive. More room for error. Okay? You look at your vector equation of the line, and it's just got nice points. Okay? When we get to our Cartesian form, and this is what I want to show you, if you get to your Cartesian form and you solve for y, okay? So how could I solve for y? Well, I could cross multiply here to get negative 4x plus 8 equals 3y minus 15. 3y is equal to negative 4x plus 23. And divide by 3. And we get our y equals mx plus b form from the vector equation as well. And that's why the Cartesian form is called the Cartesian form. Cartesian because another name for the grid that you graph everything on is called the Cartesian plane. Okay? That comes from a famous mathematician, Descartes. I don't know why they didn't call it Descartesian. Maybe it just didn't sound as cool. Yeah? No, that's in a three-dimensional. Cartesian plane is like just an XY plane.
Is that like a complex plane?
It's just a three-dimensional. I don't know what you would call. Got to have. It would probably have a name. And it's not a plane because a plane is a two-dimensional, right? You can't have a three-dimensional plane. That would be like having a two-dimensional line, right?
It's possible.
Okay. Find the vector equation of line passing through the point 2, 5 and perpendicular to the vector 3i plus j. So if you have this vector 3, 1, give me an example of something perpendicular to 3, 1. And what did negative 1, 3? Or 1, negative 3? Or any multiple of that. So this connects to our idea of slopes being negative reciprocals of each other. So with vectors, same thing. I can take that and do the negative reciprocal. How do I show that something's perpendicular with vectors? The dot product would be equal to 0. So if we multiply corresponding components and add them, sure enough, this is equal to 0. So our vector equation of our line, in this case, will be, take any point, we still have the point 2, 5, plus any parameter, and that's the direction. Again, graphically, what does this mean? Here's my point 2, 5. I need every point on that line going along the direction -1, so down 1 over 3. This is my direction vector along that line. Okay? What the parameter t says is I can make this direction vector as short or as long as I want. Ooh, this is kind of fun. This works out pretty good. And then I'll get anywhere else on that line. And if I multiply it by a negative, it will go in the opposite direction and get any other point on that line. And so by starting at 2, 5 and going any multiple of this vector will end anywhere on that line. Now our parametric form, our x coordinates are 2 minus t, our y coordinates are 5 plus 3t. And our Cartesian, solving, I'll put it over -1. You could simplify that if you want, but it just follows the same format of solving for t, subtract the number, and divide. Here's our Cartesian form. Of course, if you multiply that out, simplify it, and solve for y, you'll get y equals mx plus b. You want to make it y equals mx plus b? Okay. So I would multiply both sides, so we get 3x minus 6 equals -y plus 5. And y is equal to -3x plus 11. Oh, I drew my vector wrong. My diagram. -1. I should have gone -1 here, down -1. This direction be -1, up 3. This should be my slope. Close enough? There we go. Perfect. Just rotate your graph. Graph wasn't drawn to scale to begin with. That's what we're going to argue. But now we can still do that. Oh, no, just wait for it. That's better. Now we have 2 points. When you did this back in grade 10, you had to use your slope formula to find what the slope was between those 2 points. And then you had to go to y equals mx plus b and figure out your formula. Here, if I want to find my direction vector will be from A to B. There's my vector A, there's my vector B. If I want to go from A to B, I'm going to need to go -A plus B. And that's why it's often written, like textbooks will always write A to B is B minus A. I personally, looking at the diagram, this makes more sense to me from the diagram. And it means the same thing. So -A, -1, 4, plus b, 5, 8, is equal to 4, 4. So my direction vector is 4, 4. And then to find my equation, my vector equation of the line, I can choose any point. So I could choose 1, 4 or 5, 8 to go here. It doesn't matter. I typically choose the first one. And then we need to go plus t times the direction vector. So I would normally put in my direction vector, what number's here? 4, 4, because that's what I found out, right? Would it be wrong if I put 7, 7? Can you see that that's the same slope? In fact, 4 over 4 as a slope would reduce to 1 over 1. I'm not going to put 7, 7 because you're going to look back in your notes later and go, what the? So let's put 4 over 4 because that's what we figured out. But really, you could simplify that, or you could factor out a 4 and make that 1, 1. And then that 4 just gets blended into that parameter t, because t can be anything. Yeah. So our parametric equations would be our x component is 1 plus 4t. Our y component is 4 plus 4t. And again, had you changed that direction vector to 1, 1, then you could have your parametric equations be 1 plus t and 4 plus t. Oh, I got my mail coming. I should shut my mail down. And then our Cartesian form. And in our Cartesian form, you're going to see where those 4's can disappear. So you would have x minus 1 divided by 4 equals y minus 4 divided by 4. What would happen if I multiplied both sides by 4? They're gone. Those 4's. Y equals x plus 3 is your equation in y equals mx plus b form. For the Cartesian, you don't need to simplify that. You can leave it as the one fraction equal to the other fraction. So finding your direction vector is like finding your slope. And then you just take any point on your line to make your equation. So the vector equation of line is very easy to use and also very easy to move into 3 dimensions. So now I've got 2 points in a 3-dimensional plane, in a 3-dimensional space. And so if I want to go from P to Q, this will be my direction vector. I would have to go first negative P and then plus Q. Again, I like to write it that way. Most textbooks would just write Q minus P. Adding them up together, our direction vector is going to be 1, negative 5, negative 7. And our vector equation of a line, pick either of those points, 1, 5, 3, plus t, 1, negative 5, negative 7. And we could write our parametric and Cartesian forms of this line as well. But we won't. Well, we will eventually for different questions. Now, part B says, does this point lie on the line? -1, 3, 5. So I'm going to just continue. And put this here for us. Is that point on the line? Well, if that point is on the line, then there has to exist a value of t that makes this work. So in other words, this is where we do look at our parametric equations. I would have to have something for my x-coordinate that 1 plus t has to equal -1. My y-coordinate, which is 5 minus 5t, would have to equal 3. And for my z-coordinate, I need the same value of t, so that 3 minus 7t would equal 5. Okay? It's not going to work because from the first equation, if you solve this and you put -1 in, you would find out that t would have to equal -2. But when I plug -2 into the other parametric equations, 5 plus 10 is 15, it doesn't work. And 3 plus 14 is 17, it doesn't work. So your value of t, once you set up your parametric equations and you solve for t in one of them, that value of t would have to work for all of them for that point to be on the line. Because you would need to go in that direction a certain length to get to a point on the line. Yes? You can show that they're not equal. You could solve every single one? Okay. This works, right? Because this is the only value of t, that works, and then by plugging it in, so what I'm doing, if t is equal to -2, then y has to be 15, but y is supposed to be 3. And that's bad. So we can say that is not on the line because there does not exist a parameter t that works for all of them. Yeah.
If we're doing it like the way that we did this year, if we solve two of them, like just getting t, and then they're not the same, we just stop.
You can stop because that automatically shows that you get to those different values at different times, but not at the same time. Okay? I like what I did in part C here. Okay? 3, -5, 5. So I'll go back to here. This goes against all conventional teaching strategies. 3, -5, 5. So if we look at our parametric equations, where our x-coordinate's 1 plus t, our y-coordinate's 5 minus 5t, and our z-coordinate is 3 minus 7t, this implies that t would have to be 2. And if you plug it into the second one, 5 minus 10, that works. And if you plug it into the third one, 3 minus 14, doesn't work. And so this point is also not on the line.
Do you have a D question where we could actually get a point on the line?
No. See, I go against conventional teaching, right? Usually conventional teaching would have like, here's how to do it, here's one that works, here's one that doesn't work. So, you see, you're so used to that. So I think it's good to teach you that sometimes you can just make sure.
Just like looking at the directions.
See?
And it doesn't matter.
Mess with your, it's like, oh. So,
How are we supposed to know what a good looks like now?
when it didn't, well, if it was good, what would I have to have? What would this be? If it was good, instead of having
14,
then it would all work, right?
Nice. Like, what if you just, on the question, just erased it, put a negative on it?
You just change the question halfway through.
Get some whiteout out. Okay, there we go. Let's change this question to 1 plus 1. 8 points.
All right, well, we'll end. Well, you want to do one more?
I already did, like, let's just finish. I already did them all.
You'll